Time for a quick introduction to molecules. We've talked about atoms a little bit. We'll do a lot more of that. But to talk about a lot of substances, a lot of really interesting substances, we're going to need to think about molecules as well. Okay, a molecule is, gosh, often thought of as being the sort of parallel to an atom, but for a compound. Okay, so if I take water, for example, you all know the formula for water is H2O, right? That means it's got both hydrogen and oxygen in it. That makes it a compound in chemistry book terms because it's more than one element, right? And so a molecule of water would be a single one of those H2O units, two hydrogen atoms and one oxygen atom held together to make a water molecule. Okay, in the definition on the slide there that comes from the glossary of the textbook, you'll notice that it says it includes elements there. That's a little bit fuzzy and needs some explanation, perhaps. We said earlier that an atom was the smallest particle of an element that could retain all its properties and still identify itself basically as being that particular element. There are elements, nitrogen and oxygen are two of them, for example, that come definitely in molecules, right? Those are N2 and O2. You probably know that or remember that from high school chemistry. That means that they travel around in pairs. And so if I have two nitrogen atoms held together by a chemical bond, that's a nitrogen molecule, right? And so that's why element also appears in our particular definition. The figure here is just sort of a random thing that has some molecules shown in it. To be honest, it's some water molecules arranged in a structure that they would form if they were in an ice crystal. And in there, we'll look at some different ways to represent molecules in this video. In this one, the atoms are represented by balls and they're held together by sticks. The red ones are the oxygens and the much smaller white ones are the hydrogens, reflecting the fact that hydrogen atoms are in fact smaller than oxygen atoms, although not by as much as those pictures imply, I think I would say. Okay, so that's just a first look at molecules. Our main purposes today are to talk about ways that we might depict or represent molecules, because we'll be seeing a variety of those as we work through the class. Okay, so molecules represented by molecular formulas, that's one way we can describe a molecule, right? The example I stuck with here is, again, water. And so if you look at the water molecule sitting there, we can see down below that there's a formula H2O, where the 2 is a subscript. That subscript tells us how many of that particular element there are. Where there's not a subscript written, like on the O, that means there's just one of them. Okay. This picture is what is known as a space filling model, where the balls that represent the atoms have just actually been smushed together. It arguably gives a little better idea of what a molecule might look like if we could shrink down there. A little bit of a note about the way molecules are shown in your textbook. The textbook, we do try to use a consistent color code throughout, and I've tried to stick with that here. So in the textbook, if you're looking at these little molecular cartoons, the red ones are oxygens and the white ones are hydrogens, black ones are carbon, for example. Blue ones are nitrogen. That doesn't mean that oxygen atoms really are red or anything like that, because they're very definitely not. But that's just a handy way of keeping score, if you want, and counting things up in the pictures. Okay. So that formula, the H2O, tells us the composition. It tells us exactly what ratio of things are in that molecule. Going forward, we'll, before long, look at how to take that and use that idea to be able to identify substances, say. If we can measure how much of each element is in them, we can figure out what their formulas are, all right? We also could talk about the mass of a molecule. And because the molecule is made up of atoms, if I know the masses of atoms, which we do, right, we know how to look those up in the periodic table. So we could look up the masses of our hydrogen and oxygen atoms and say in AMUs, the units we've been using for that, hydrogen is almost exactly 1 and oxygen is almost exactly 16. So we could say that the mass of a water molecule, therefore, should be 18, right? Because it's 2 hydrogens and 1 oxygen. I get 16 plus 1 plus 1, and I get 18 for that. So that would be the mass in AMUs of a single water molecule. There's a lot of ways to talk about molecules, and we're going to do a quick run through here just because we'll be seeing different ones both when I'm showing you things in class and when you're reading in the textbook. One way to talk about molecules is by name. Molecules have names, and if I'm talking about molecules with my chemist friends, then we might very well refer to a lot of molecules by name, saying that, like, well, we'll just know what that means, and then it's a nice simple way to talk about things, okay? I usually don't rely too much much on you all being able to recognize names of molecules, okay? There are some notable exceptions to that. If I say water, I'm going to expect you to recognize that that's H2O. If I say carbon dioxide, that's not very hard to figure out. That's carbon and 2 oxygens, so it's CO2, right? But other molecules, I'm going to be less thinking that you're just going to know the names or recognize them. I don't really expect you to memorize the names of lots of molecules or anything like that. So if I were talking about a molecule by name, sometimes they still have more than one name, to be honest, because there's some older naming systems that don't go away easily. The molecule that's in the examples I'm doing here is ethanol, also known as ethyl alcohol. That's got the formula that is shown below. And you'll see I've written the formula 3 different ways here. I've written C2H6O. That's what we might call the simplest possible formula for this molecule. It just tells us how many of each atom, okay? It says I've got 2 carbons, I've got 6 hydrogens, and I've got 1 oxygen. It doesn't tell me anything about how they might be hooked together, but it says those are the atoms that are in there. Sometimes you might see this formula written in the second form that's there that says C2H5OH. Okay, that piece does a couple things. The biggest thing it does is it separates out that OH group and puts it on the end there. Okay, if we know a little bit about chemistry, then we might know, for example, that molecules like that have some carbon atoms and then have an OH group, those often collectively, those are known as alcohols. Okay, this one is ethyl alcohol. That's ethanol. That's the alcoholic component of alcoholic beverages, for one thing. It's also the alcohol generally that, like if you're getting a shot at the doctor's office, that they rub your arm down with before that. There's propanol, which if you buy rubbing alcohol in the grocery store, that's propanol. That's got 3 carbons instead of 2 carbons, and it's got a longer chain. If I want to get even more information about how the atoms are hooked together, I could go to this third formula out here, right? This one says it's CH3CH2OH. That's starting to tell me what the molecule would look like. So that says take a carbon and attach it to 3 hydrogens, then take that carbon, hook it to the next carbon, hang 2 hydrogens on that carbon, and then put the OH on the end of that. Okay, so again, if I know a little bit about chemistry, if I see that CH3CH2OH, it's very easy to picture what the molecule would look like. Okay. Students often ask, well, you know, why are there 3 different formulas there? Which one is correct? Unfortunately, I know this is the kind of answer you hate, but there's not a right formula and a wrong formula there. It really just depends what kind of information we're trying to convey. Right? Any one of those formulas is a perfectly acceptable representation of ethanol. I guess I would argue that they have progressively more information in them as they go from left to right, but that doesn't make the other ones wrong or anything like that. Other ways to depict molecules, there are what are called structural drawings or line structures, and we're going to talk about those momentarily because that's one of the things that a lot of people don't necessarily get taught at all in high school chemistry. I know a lot of you feel like there's lots of things that you got taught in high school chemistry that you're not convinced you learned or that you remember. These line drawings are one that a lot of you, to the best of my knowledge, just don't generally get taught. So we'll spend a minute in doing that. They're pretty easy to do. That's the good news about them. And then we can get actual models, which might be in software, like some of the pictures we're looking at here, or they might be real 3-dimensional things where, you know, you just take out balls and connect them with sticks and stuff like that and make models of molecules. If you have friends that are taking organic chemistry, there's a good chance they'll end up with a model kit for that because it's the best way to be able to sort out which structures go with which names of molecules and things like that when there are some complicated looking molecules around. So here are some examples of ways we might do this. On the top, I've got my ethanol molecule, right, with 2 out of the 3 formulas that I had written before on the previous slide written along with it, okay? Now, if you look in let's try this. Now, if you look at this picture over here, you can see here, that's that first one, the gray atoms here are the carbons. That's my first carbon. In this formula, that's the carbon down here because it's the one that's in a CH3. I know that because here's carbon and here are 1, 2, 3 hydrogens that are attached to it. All right, so those things, that's my CH3 piece. It's attached to this carbon, which is attached to 2 hydrogens. So that's the CH2 piece over here. And then I have the red one is the O, and there's my H, right? So that's my CH3, CH2OH. And this is what that might look like if I was molecule sized and could actually see it. On the bottom, notice I've got a different looking molecule. This one is dimethyl ether. It is very definitely not something that wants to be the component of a beverage or anything like that. But it does have the same overall formula, C2H6O. All right. So this is an example of why we might choose to use one of those more informative formulas, is to make sure we know what the heck we're talking about, right? This one has the formula, the more structural information would tell me it's CH3O CH3. So now I've got two of these CH3 pieces. Here's my carbon, my 3 hydrogens, and then here's my other carbon with its 3 hydrogens, and they're connected by this O as a bridge in the middle, okay? So if I just measured how many of each atom are in there, I wouldn't be able to tell those two molecules apart, right? I could say, well, it could be either one of these. I'd have to know some other things, measure some chemical properties, say, to be able to distinguish between them. All right. And again, that's a pretty good example of why it's sometimes handy to write the formulas in ways that contain more information, as opposed to just going for the simplest counting up the atoms version of things. This one is just a handful of molecules. These are actually figures that are in the textbook, I believe, that I lifted from there to slap in here. They do show us some just different ways to represent things, okay? A lot of the molecules here are in this so-called ball and stick format, okay? The left-hand side, we've got some small molecules, water on top. The one in the middle is carbon dioxide, and you can see this particular drawing or model has some information about the molecule. It's got 2 sticks here connecting my carbons and my oxygens, and that tells us a bit about how the bonds are. If you remember some high school chemistry, you might remember that's what's known as a double bond, because it's got a stronger bond in there than it would if it was just what we call a single bond, represented by a single stick. The one on the bottom is propane, C3H8. And so that's the beginnings of making things into longer chains, which is something carbon is very fond of doing, right? Propane, gosh, if you have a gas grill in your yard, that's the gas that is burning in your gas grill in most cases, all right? On the right-hand side, we have a couple of models of pieces of polyethylene molecules, right? If you've been reading in your textbook, chapter 2 talks a lot about polymers, which are, gosh, in real life, you think of them as plastics for the most part. But in chemistry viewpoint, they're really long chain molecules, just thousands and thousands of atoms hooked together. Those are 2 different views of polyethylene. The top one is this so-called space-filling model, where the white sort of half spheres on there represent the hydrogen atoms in this case, and the black ones represent carbon. So we didn't really follow the same thing there. Wait, no, those are the right colors. I'm sorry. The bottom is the ball and stick model, where you can actually see the bonds a little bit better, right? Polyethylene is a really interesting substance because its properties depend tremendously on how long the chains are and how straight the chains are. And in fact, polyethylene can be used, well, it is used for making milk jugs. If you go to the supermarket and buy a gallon of milk, that jug that it comes in is made out of polyethylene. At the same time, polyethylene can be used as filling in bulletproof vests. People nowadays make artificial ice rinks are sometimes made out of polyethylene. I, alas, have had both of my hips replaced, and there's polyethylene components in the replacement joints because it's a very hard and durable material that the other pieces just slide across really easily. And so there's a lot of variation in properties there, which is something it's kind of where some engineering ideas come into doing this, right? Where you can say, well, if you can make this molecule in this particular way, then it'll have these different properties, and we can start to make these different objects or applications out of it. All right, as I said, this idea of line drawings is one that will be new to a lot of you. And so let's take a moment and work on that for the rest of this segment, okay? So this is one that honestly nobody would use the line drawing for ethanol, which is what I'm going to do here. But it's a nice, simple place to start, okay? So the idea here is there's lots of molecules in the world that contain large numbers of carbon and hydrogen atoms. This is, again, what's called organic chemistry, the chemistry of compounds of carbon. Those include a lot of the compounds that are present in your body, a lot of pharmaceutical compounds, things like that. Because of that, the structures can get complicated because these molecules can have very long chains, and it's important to have a way to depict what they would look like, okay? So this is kind of a shorthand notation, a way to make a nice visual representation that's not terribly cluttered and shows us something about what the molecule would look like. There are really just a couple of rules here. Okay. Number one is that carbon atoms and hydrogens that are attached to carbon atoms are not shown in the pictures. Okay. And again, let me emphasize that that says hydrogens that are attached to carbon atoms. Okay. Those are not shown in these line drawing pictures. Every place there's a line, that's a chemical bond. Okay. Carbon is a very, very nicely behaving element. Every carbon atom in every one of these structures will always have exactly 4 bonds. Okay. So if I want to go from knowing that this is what the molecule looks like, right? So this is here's my CH3, here's my CH2, and here's my OH, the way we've been writing it, right? I'm going to take the carbon atoms and I'm going to just put the bond that connects them in the picture, okay? So over here, where this CH3 is, I'm not going to show any of those H's because they're attached to the carbon. I'm not going to write a C for the carbon, but I am going to say there's a bond. So this bond here, that first line, is that bond in the molecule, okay? I get to the CH2 carbon, this one here. Again, I'm not writing a C and I'm not writing the H's, but this bond coming out of the other side, that's now this bond in this picture. And then I get to the OH. The O is not a carbon or a hydrogen attached to a carbon, so it gets written. And the H is not a carbon, and it's also not a hydrogen attached to a carbon, so it gets written. Okay, that says that's what my structure would look like. All right, suppose I came across that figure, let's just erase those things. Suppose I came across the figure over here and I wanted to decode it to make it into a formula. The way I'm going to do that is every place where there's a corner, an intersection of 2 or more lines, or an end of a line, I'm going to write a carbon. So I put a carbon there and I put a carbon there. Every carbon has to have 4 bonds, right? That's the rule on the bottom. So every place there's not 4 lines coming out of a carbon, I'm going to add enough hydrogens to bring that number up to 4. So I'm going to say this one needs a hydrogen and another hydrogen. I'm going to say this one over here needs 3 hydrogens. It doesn't really matter where I put them. I'm just writing them in so I could count them up, say. All right, so that would get me back to something that looks, at least in terms of counting up the atoms, like the one on the left. All right. Again, for ethanol, this would be more trouble than it's worth. But for other molecules that are bigger and more complicated, this is really handy, right? One place, if you haven't seen these in chemistry class, if you ever pay attention when you open like a medication, whether it's a prescription or an over-the-counter medication, if you ever read the little information sheet that's in there, there's usually a picture of a structure of the molecule that's the active ingredient. And it usually is in this line drawing form, okay? So this is a molecule that's a little bit more complicated looking, I think you'll agree. This particular one I just read about recently, and it's a compound that's been used to make adhesives, like you might use for Post-it notes, things that just stick when you push on them. In this case, to make those using more renewable resources, so from plant-based materials, essentially, okay? And so what we're going to do is we're going to take that structural formula and we're going to walk through finding the formula. I'm going to do this one. We'll do some more of these in a class session coming up soon. Okay. So here's my picture. Every place there's an end of a line or an intersection between 2 or more lines, I'm going to put a carbon. So I'm going to put a carbon there because that's an end of a line. This one is an end of 2 lines, but that's still a carbon. Here is an intersection point, so that's a carbon. Another intersection point, carbon. The ones that have oxygens there, I'm going to skip over that because I can't put a carbon there because it's an oxygen, right? Carbon, big 4-way intersection there. Carbon on all the corners of this hexagonal ring. And then I'm going to get a carbon over there, all right? So that should get all the carbons in my picture. Next up, I want to add hydrogens, enough hydrogens to make sure that every carbon has 4 lines coming out of it. All right. When I do that, I'm just going to, again, just write in the hydrogens so I know how many there are. I'm not going to be too careful about where I put them or what angles I write them at, because that's something we'll learn about later, is how they would really want to look. Okay. Out here, this carbon has already got 2 bonds coming out of it because it's got 2 lines. So it gets 2 more hydrogens. Notice that brings its total number of lines coming out of that carbon up to 4. So that means it's done. This one here is already done because it's got 4 lines already, right? So no hydrogens for it. Next, I'm going to draw in 3 hydrogens here. This one looks good already because it's got 4 lines. I'm not going to put any hydrogens on the oxygen, okay? Because the only hydrogens that are not written are the ones that are on carbon. Okay, so if there was a hydrogen attached to any of those oxygens, it would have to be shown in the picture like the OH was in the previous one. Okay, so I'm only adding hydrogens to the carbon atoms. That's important. Up here, I'm going to get one up there, and I'll put the other one down here because I need two. In my ring, I've got 1, 2, 3 places where I have 3 lines coming together. So I need a fourth one there. The other 3 corners, this one, and this one, those all have 4 lines already, so they're happy. And down here, I have a 2-bond carbon, so I need 2 more. To make this into a formula, all I have to now be able to do is to count. Okay, and so let's see. We're going to write the carbons first. Normally for these organic molecules, we write the carbons first, then the hydrogens, then we tend to write everything else in alphabetical order. Okay, so that's what I'm going to go with here. Let's count up the carbons. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 11, and that one is 12. I'm going to do the hydrogens next. Okay. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then I'm going to count the oxygens. I'm not going to forget them, even though I didn't write them. Okay, that's something people do sometimes, is forget about the elements they didn't have anything to do with. In this case, it looks like we've got 1 up there, 1 here, and 1 there. So we've got 3 oxygens in the, 4, I missed 1. Okay, let's change that to a 4. See, and I told myself I could do this without having a set of notes by me to cheat from. All right, we'll do that and we'll make that a 4. I did kind of think it was supposed to be a 4, but I was just not seeing the other atom there, okay? All right, so that should be my, my formula then, all right? And so that's all there is to it. And that gets me a formula for this particular compound. If you haven't done those, like I said, we'll do 1 or 2 in class session, and I'll make sure there's something in one of your homework assignments. If you look in the back of chapter 2 in the textbook, you'll find some molecules that you could practice on as well. As you can see, it's not hard. If you can count to 4, you can do this, okay? And so it's just something to get a little bit of practice with. The main things people sometimes have a little bit of trouble getting used to is avoiding writing hydrogens that are attached to things other than carbons.